Hello AP Physics 1 students. Alright, so now that we have our equation for the magnetic force on a moving point charge, and we have our right-hand rule for figuring out the direction, our way of showing three-dimensional vectors, let's try some problems. Let's turn to our problem set, and here's problem number 1. Go ahead and read it, and all I want you to do is the math for parts A, B, C, and D. You're really going to be doing the same thing over and over. I'll even get you started. Of course, we're going to be using QVB sine theta. It's the only equation we have. But we're really just changing the angle every single time. So once you write out the work for one, you really don't have to show the work for all the others. You know, in class, you just want to get things done, just crunch some numbers, get a sense of the numbers involved, and then we'll come back and talk about the answers as well as the right-hand rule. So right now, just do the math, then come back to see the answers. Okay, so first of all, you should notice that the charge is given in microcoulombs. You know my advice is always just replace the metric prefix with its power of 10. So just write 2 times 10 to the negative 6 coulombs. Here's the velocity, here's the magnetic field. It's a 90-degree angle. We measure an angle theta between V and B, and this charge is moving to the top of the page. Magnetic field is to the right. That's a 90-degree angle, plus it's given here is 90 degrees. So it should be no difficulty here getting 0.32 newtons, right? And just in case you got that wrong, try it again. And now we're just changing the angle each time. We're going to use 2 sig figs for everything. You should have no trouble getting these magnitudes of the forces, 0.23, 0.16, and then finally 0 newtons. All right, now let's talk about the right-hand rule and doing to figure out the direction of the force. So let's try this together. For this first one here, which way is the charge moving? It's moving to the top of the screen, right? On your page, if you have your paper on flat in front of you, your fingers should be pointing directly away from you. It would be up in my plane of view, but we're not going to use up or down. We're going to say to the top of the page, right? And now the magnetic field is pointing to the right. So you're going to rotate your wrist so that your finger is still pointing directly away from you. Now, if you have it so that your fingers are trying to curl in a way that's, I don't know, painful for you, you're doing it wrong. You shouldn't have to rotate, you shouldn't have to bend your wrist, you're just rotating the wrist. And so your fingers should be curling to the right. When you stick your thumb out, your thumb should be pointing directly into your paper. Yes, I know that would be down for you, but if you're doing it from my perspective, that's away from me, and we can't say up or down. That's confusing, so we're going to say into the page. How do we show into the page? Well, that's going to be the X. Now here's a picture of my right hand, just in case you're confused about it, right? So from my perspective, the charge is moving to the top of my screen. My fingers are curled to the right, away, so the right this way. My thumb is pointing directly into the screen. This is I think, the best way I could show this to you without being live and in person in front of you, right? And so your hand should look sort of like this. If instead your fingers were curling the other way, you're confused and your magnetic field should be pointing to the right. If you have your thumb pointing towards you and you're trying to curl your fingers away from you to the right, that seems painful, this seems wrong. In the end, your thumb should be pointing into the paper, and we show that with an X. You can put the circle around the X if you'd like to, that's sort of optional. The important part is the X. That would mean directly away from you into your paper. When you try it for the second part, now your fingers should be pointing to the top right-hand corner of your paper, the magnetic field is still to the right, and your thumb is still pointing into the page. So again, we have an X. By the same token, we do it for letter C, we're still going to get an X. For the last one, well, there's no direction on 0, so it's just going to be 0. But what we learned from this, as we showed from the original example, is that if a charge moves directly with the field, the angle is 0 degrees, sine of 0 is 0. Or if you try to do it with your right hand, your fingers are already pointing to the right. The field is also to the right, which means there's no preferred direction for your hand, and there's no curl to it, right? You don't have to curl your fingers any way at all, and so there's no magnetic force. And so what we learn is that if a charge moves directly with the field, it experiences no magnetic force. Or if the charge moves directly against the field, what would the angle be? Well, it's between V and B. That would be a 180-degree angle. What's sine of 180? That's 0 also. So it feels no magnetic force. Basically, a charge has to somehow cut across field lines to feel a magnetic force. If it moves directly with the field or directly against the field, it feels no magnetic force at all. All right, let's go ahead to problem 2. Go ahead and read it. I want you to do the math, find the magnitude of the magnetic force, come back to see what I got, then we'll talk about the right-hand rule. Okay, so of course we're using QVB sine theta. It's millicoulombs. Power 10 there is 10 to the negative third. Velocity is given, magnetic field strength is given, and then alpha here is given as 30 degrees. However, look at the definition. In the equation, we define theta as the angle between velocity and magnetic field. That's not alpha at all. It's this from here to here. That's theta over here. 30 degrees is not the correct angle to put in here. In fact, it's the supplement of 30 degrees, which is 150 degrees. The angle theta in here is 150 degrees. Now, You should know your rules for trigonometric functions, and we should know that sine of 150 and sine of 30 give the same answer. And so yes, if you put 30 degrees in here, you'll get the same answer, but technically it's not correct. Theta is defined from velocity to magnetic fields. That's going to be the 150 degrees. Any way you do it, you should be getting 810 newtons. Okay, so at this point, if you have not yet tried the right-hand rule, go try it on your own. So your pointer finger is pointing to the top left corner of your page. You curl your fingers all the way to the bottom of the page, which is basically sort of curling towards you, right? And then you stick your thumb out. Your thumb is pointing out of the page. How do we draw out of the page? That's the dot. The circle around it is the optional part, but the dot is the important part. If you didn't get that, try it again on your own. Now, if you say your thumb is pointing up, you're not necessarily wrong, but if I'm doing it from the perspective of my screen, and if you're doing it with the screen as well, your thumb will be pointing towards you, and up and towards you are not the same thing. So you have to go with this convention that we're not going to use the words up or down. We're going to say, in this case, out of the page or out of the screen, and that's going to be the dot. All right, let's go ahead to problem 3. Again, same deal. Do the math, get your answer, try the right-hand rule, come back to see what you get. Once again, notice this is millicoulombs, so it's 10 negative third. Using QVB sine theta, we should be getting 0.045 newtons. Everything's 2 sig figs, only 2 sig figs in your answer. Okay, what's the direction? Well, in this case, the charge is moving to the bottom of the page. We're not going to say down. It's moving to the bottom of the page, so you start with your fingers pointing directly towards you. The magnetic field is pointing to the left, so you got to twist your wrist. It's kind of uncomfortable. Maybe put your fingers maybe sort of pointing towards your own face, so you can comfortably curl the rest of your fingers to your left. And now your thumb is pointing which way? Down, but we can't say down. It's into the page, right? It should be pointing directly into your page. But that's not the correct answer. The correct answer is out of the page. Why is that? Well, if you've been paying attention in your notes, you should have written that we start with our fingers pointing the direction of the motion of positive charges, but this is not a positive charge, it's a negative charge. So what do? Well, in the end, you just change your answer, right? So you do your right-hand rule like normal, and then if you should be getting into the page, you change your answer to out of the page. Alternatively, you could say a negative charge moving to the bottom of the page, that's like a positive charge moving to the top of the page. So go ahead and try the right-hand rule that way, with your fingers pointing directly away from you to the top of the page, and then your fingers curl to your left. Now your thumb points out of the page, which is the correct answer. So you could change your force in the end, right? Do the right-hand rule like normal, and just change the direction of your thumb, the opposite direction. Or you could imagine a negative charge moving the opposite direction and be a positive charge. Or you could use your... Now, if you were in front of me, you'd see I'm mouthing the words left hand, but I don't say it because it's funnier that way, right? And so we're using our right-hand rule, but if you do use your... You could get it correct if you use your... Whispering is right? Because if you use your other hand with a negative charge, you get the right answer. But I don't like to do that. I always like to use my right hand, so I'm always doing the same thing every single time. In this case, just flip something. Flip the answer for the force, for the direction of the velocity, but you have to flip something to get the right answer for a negative charge. And this is kind of the only trick they could possibly play on you, by giving you the wrong sort of charge. Just be aware of that. We use right-hand rule for the motion of positive charges, right? And so you got to flip something to get the answer if it's a negative charge. Easy fix. Okay, in our notes, let's look at one more example of right-hand rule. So I want you to draw a uniform magnetic field pointing to the top of the page. All these blue lines here are showing to the top of the page, so they're all denoted by magnetic field. We got a positive point charge that's moving directly to the right. Pause the video, do a quick right-hand rule, figure out the direction of the magnetic force. Okay, you should have no trouble getting that is out of the page. And by the way, with any of these, if you're finding yourself contorting yourself and it's really difficult for you to do, you know what you could do? Just turn your page. You can turn your page any way you want to make it easier for you to do the right-hand rule, rather than getting carpal tunnel syndrome doing all these right-hand rules. And then just make sure you turn your page back before you start to write some numbers or answers there, because test grader on the AP exam or I is not going to try to read things that are upside down. All right, so we should have no problem getting a magnetic force out of the page. Now, it's very unlikely this positive charge comes all by itself. So what if there's a whole bunch of positive charges that are all moving to the right? A whole bunch of positive charges moving to the right. Maybe they're protons. That sounds like maybe like a current. Let's draw an imaginary wire around all these positive charges moving to the right. A wire of length lowercase l. Let's see what happens. Well, by QVB sine theta, each one of these positive charges feel a magnetic force out of the page. They're all going to hit the wire, and the whole wire, as one object, will feel a magnetic force out of the page. Let's develop an equation for this magnetic force. we can say that, let's say they're moving at a pretty much a constant speed, as we talked about back in circuits, that charges pretty much move at a constant speed through the wire in a current, and so we'll replace V as V bar as delta x over T, but delta x is just the length of the wire, so replace V, which is really V bar, as L over T. You might notice here is Q over T. What's Q over T? Well, that's just current. And so here we have ILB sine theta. So the whole wire with current will feel a magnetic force, in this case, out of the page. It's going to jump out towards you, basically. Let's go ahead and box that in. Once again, however, we see something with a vector and a sine theta, getting a vector as an answer, which means there must be another vector in here, which means there must be another cross product. This is the cross product IL cross B. So what's the other vector? Well, current, remember, is a scalar, so it can't be that. It's got to be L. So it turns out L is actually the other vector. So L is a vector, B is a vector, magnetic force is a vector. Let's define our terms. So F sub m now is magnetic force on a current-carrying wire. So we have to know which force equation to use when. QVB sine theta was for an individual point charge. ILB sine theta is for a whole wire of length L with a current inside of it. I is the current in the wire experiencing the magnetic force. You know, anytime we deal with forces or fields, we always have to be very careful defining what plays what role. So this current here is the current experiencing the magnetic force. L is the length of the wire, and in this case it's going to be a vector that points to the direction of conventional current. Think about it as the velocity vector along the length of the wire, although, that's rather confusing, but in this case it is. So something has to be a vector, and we did define very carefully the current is a scalar, so we're going to say it's this, right? So it's a vector that points to the direction of conventional current. This way, we're still following the flow of positive charge. We don't have to change anything about our right-hand rule. Capital B is, again, the external magnetic field produced by some magnet that we don't even know where it is. We don't know what's producing it. Doesn't really matter. Theta, again, is in the equation, and so in this case, it's the angle between L, which, again, is really just showing the direction of the flow of positive charge, and the magnetic field, the external magnetic field. And so we use this equation for the force on an entire wire, feeling the force all as one object. For the right-hand rule, it's exactly the same as before. Our pointer finger points to the direction of L, which is the direction of the conventional current, the direction of positive charge moving. We curl towards B, and the thumb is the magnetic force. So basically, it's the exact same thing as before, but in a problem, you have to choose the right equation. QVB sine theta is for a point charge, ILB sine theta is for a wire with current. And while usually it's going to be very, very obvious, once in a while you'll have a mix and a match of the two different sort of objects. Just make sure you're picking the right equation for the right situation.